Hello and welcome to Sunday's edition of Cracking the Cryptic, where today we're going to mark a debut on the channel for a set called Mimaamakim. I think Mimaamakim, is that a thing? A Mimaamakim? I'm probably going to say that wrong a lot, but it's called Triple Decker, this one. And this got some very interesting feedback from the testers who said it's basically a work of genius, but it is incredibly hard. So this might be a long video, but we don't mind that. We love our Sudoku. So I'm looking forward to trying it. And I have allowed myself enough time that if I do mess it up and this video has to be abandoned, I can try another puzzle instead and probably still meet my 8:30 deadline. So fingers crossed. Now, before we start, thank you so much if you joined us last night for the Bubba Is You stream. We enjoyed it again. And the next stream will probably be just me attempting the music box challenge from The Witness. So look out for that. Might be Thursday night. We'll announce it on Twitter, which is @CrypticCracking, in due course. I want to say a big thank you, though, to those of you who either work for Google, who are connected with Google, who have been appealing to Google to try and have our apps, our Thermo Sudoku app and our Miracle Sudoku app, reinstated on the Google PlayStore. You may be aware, if you've watched the last couple of days of videos, that they have been withdrawn on the basis that they are repetitive. You cannot tell. Well, let me tell you, this gets my goat something rotten. There are a lot of very bad Sudoku apps out there, and our Sudoku apps are not those. They have taken an awful lot of love and care and work to get them into the state they are, which is magnificent. Each one of them featuring, handcrafted puzzles of the highest quality. And they are anything but repetitive. Indeed, yesterday we looked at a Thermo Sudoku, and the logic in it was so different to what you might see in a killer Sudoku, etc. But we just need real human beings to take a look at this and hopefully get the decision reversed. It hasn't happened yet, but we're keeping our fingers crossed, and big thanks if you have tried to help us. Anything else to mention? Yes, some of you have been enjoying Euclidean Sudoku by Butaku, this puzzle here, which it was an interesting one in the sense that it's clearly a very clever Sudoku and easily good enough to feature on the channel. But the reason we didn't do it on the channel is because it does have some quite mathematically heavy rules. Now, actually, I did try this puzzle, and there is a video of it now of me solving it on Patreon. So if you are a patron of the channel, you'll be able to access that already. And once you get your head around it, it's really not that mathematical. It's very beautiful and an incredibly clever puzzle. So do have a go. There'll be a link to have a go at the puzzle under this video. And as I say, if you get stuck, you can watch me have a go at it over on Patreon right now. Apart from that, I've got nothing else to tell you. So let's get on with Triple Decker, and I'll read you the rules. So normal Sudoku rules apply. Digits along each line must be a set of consecutive digits in any order and must not repeat. So these lines in the grid are all so-called Renban lines. You have to excuse me if I cough a little today. Still getting over this illness. So how could this look? Let's make this a 7 and this a 5. Then we would know this square would have to be a 6, because together they must form a consecutive sequence. They don't have to be in order, so they don't have to be 5, 6, 7. It's not like a thermometer. They can be in any order, but they do have to be consecutive. Clues outside the grid give the sum of the digits sandwiched between the 1 and the 9 in that row column. So this is our old friend Sandwich Sudoku. How does it work? We don't actually have many sandwich clues, and they are very large sandwich clues, but let's ignore the fact they're large. This 33 is telling you that between the 1 and the 9 in this column, let's put the 9 here and the 1 here, these 5 cells would have to sum up to 33, i.e. the cells sandwiched between the 1 and the 9 would have to sum up to 33. You can make your own mind up about whether this example is any good or not. It might not be. Other than that, inequality signs point to the smaller digit of the two connected cells. So we've got 2 inequality signs, and that's all, which is a remarkably scant rule set, isn't it? We've got 3 sandwich clues, some Renbans arranged in these sort of weird Windoku shapes, Windoku being a sort of form of Sudoku. I don't know how many of you have seen it, but there are some Sudokus out there, and they became popular in the early days of Sudoku, where these outlined blue cells would be like extra regions. You'd have to put the digits 1 to 9 in there, and the digits 1 to 9 in there, and that's sort of what this puzzle reminds me of. But anyway, do have a go. The way to play is to click the link under the video as usual. Now I get to play. Let's get cracking, and I'm immediately going to get cracking, I think, by looking at the sandwich clues, because when I was doing the example, I realised something. What's the absolute maximum size of a sandwich? That's a good question. Well, let's imagine we put the 1 here and the 9 here. Well, from the secret is, of course, that any row, column or box of a Sudoku, if correctly completed, will contain all of the digits from 1 to 9 once each. So, this column, in total, if we fill it correctly, adds up to 45, but the sandwich crusts add up to 10. So the maximum size of a sandwich is 35, and that means that this is almost a sandwich maximum. The only thing is, it's got to be missing a digit or digits that sum up to 2. Well, there is no way of making digits sum up to 2 in a Sudoku without repeating the digit 1. So in fact, this column must have a 2 in one of those cells, and oh no, hang on, right, I've started, well, that's true, it's absolutely true, but I'm just thinking I might have been better starting here, actually, because the juxtaposition of this 33 and 32 look interesting to me. Yeah, this is where I should have started. Let's come back down here. We've got the same logic, look, applying to this row. We've got a 33 clue, so we know there's a 2 outside the sandwich sum in one of those two positions. But I think the key is going to be this 32 clue, because this 32 clue is telling us that there are cell or cells summing to 3 outside the sandwich. But remember, the sandwich crust has a 1 and a 9 in it. So this 32 must be a 3 on its own, because if we try and, for example, let's try and make these a 1 and a 9, and then if we want these two cells to add up to 3, which they would have to do, they would have to be a 1 and a 2 again, and you're going to get a repeated 1. So there is one cell outside the sandwich in column 9, and it is a 3, and we know it's not here. You can't put 3 here, because if you do, you've broken this sandwich clue, which needs a 2 exactly outside the sandwich. So this square, I think, is a 3. This square is therefore a 1 or a 9. This square is a 1 or a 9. That tells us this square is a 2. This square is a 1 or a 9. And now we can do the same logic on column 1, which is, of course, not where I should have started. And we get this pattern. The only reason I'm hesitating now is this, I think, is all correct. But it is very, very light on detail. This is crazy. I don't think I can. I'm just trying to see if I can even work out which way round these 1s and 9s go. No, I can't. The only thing I can see is that those two are the same. So if this is a 1, this will be a 9, and that will be a 1. So those two are the same. Let's just colour those in for a moment. Now that means whatever goes in here, and it is an interesting digit, it's a 1 or a 9, is forced onto a renban in that 2x2. And that's interesting, because if you get a 1 or a 9 on a renban, you know the contents of that renban. If that square was a 1, this immediately would have to be a 1, 2, 3 renban. If it's a 9, it has to be a 7, 8, 9 renban. No, I mean, this is nuts. This is absolutely nuts. I mean, am I in Cloud Cuckoo Land, or is this just ridiculous? This has a unique solution. How can this have a unique solution with these? We know just about nothing about all these renbans. Unless there is some weird trick that allows me to conclude this is a Windoku, that's not such a stupid idea. If there's some sort of set analysis that tells you that all these have to be, you know, this has to be a set of the digits 1 to 9, this has to be a set of the digits 1 to 9, then I might believe it solves. If I knew each of these was I mean, even if I knew that, I mean, a Windoku puzzle normally has given digits, more given digits than this. Even if I knew that, I'm not sure I could solve it. Oh, no, hang on, is it mod 3? Is it mod 3? Is that a silly thought? Sorry, the thing I've just realised is that any Renban line of length 3 has an interesting property, and I've looked at this property before. So let's imagine that this is filled with digits. One of the digits on this Renban will be the middle digit of the 3 digits. I'm going to call that digit x. Now, the higher digit is therefore x plus 1, and the lower digit is x minus 1. So if I sum up a 3-cell Renban line, it always sums to 3x, which means it's exactly divisible by 3. Now, there are a lot of these 3-cell Renban lines in this puzzle. So I'm just wondering if, for example, those cells together, therefore, are just a collection of Renban cells. So these 18 cells are divisible by 3. But I know that a column of a Sudoku is divisible by 3 because it sums to 45, and 45 is divisible by 3. There is a knowledge bomb for you. So if the purple cells, or some people think it's pink, but if these 18 cells are divisible by 3 and the columns overall are divisible by 3, that tells me that these cells are divisible by 3. And the same is true here, of course. Those cells are divisible by 3. And these cells are divisible by 3. Yes, they are, because it's just the same logic in the rows rather than the columns. Those cells are divisible by 3. So all of these cells, in fact, if I highlight the middle Renbans as well, all of those cells in the puzzle are divisible by 3. I'm just going to highlight all of those just for a second. All of these cells, including these, I should have highlighted those in the same colour. That's a bit of a ricket. Apologies. All of these cells are divisible by 3. Now, 3 is divisible by 3. 1 plus 9 plus 2 is equal to 12. 12 is divisible by 3. So those cells together are also mod 3, which means that these cells, because a whole Sudoku grid is divisible by 3, because it adds up to 9 lots of 45, 9 lots of 45 is 405, obviously, and it's certainly divisible by 3. Those 5 cells are divisible by 3. What does that mean? Well, I mean, I know what it means. I'm trying to work out if it means anything useful. I don't know if it does, you know. That feels like it's an incredible amount of effort to prove something that is absolutely useless. Those 5 cells are divisible by 3. I mean, I think there's a multitude of ways that could work. Bobbins. Right, apologies. Let me get rid of my highlighting because I think that was a complete red herring. I'm going to go back to my Windoku idea then. So how do I prove that each of these is a set of the digits 1 to 9? That probably is tricky. Let's try and do columns again. So those cells are 6 sets of the digits 1 to 9. So if I'm isolating these cells, I need to remove from those 6 sets of the digits 1 to 9 these cells and these cells and these cells. So they are 3 sets of the digits 1 to 9. Let me just have a look at this. This might prove to be a fool's errand as well. I just want to take a look at it and have a think for a second. So now we've got a weird relationship, because we've got the orange cells were originally 6 sets of the digits 1 to 9. The blue cells were 3 sets of the digits 1 to 9. So the orange cells are equal to 3 sets of the digits 1 to 9 plus the blue cells. That is actually, yeah, okay. I'm going to do that a bit more slowly. I can see that that is interesting, at least. At least I think it is. There's going to have to be 4 1s in the oranges. And that means we've got that, yeah, okay. Okay, I think we're onto something. Let me do that all a bit more slowly. Sorry. So what I did was I firstly highlighted all of column 2, 3, 4, 6, 7 and 8. And I want to describe the contents of those cells. Obviously I don't know how these cells are filled. You know, I don't know if there's a 1 here or a 9 here or a 5 here. We've got no clue. But in total, I do know exactly what digits are going to be in the orange cells, because it's 6 complete columns of a Sudoku. So the orange cells we could describe absolutely precisely as being 6 sets of the digits 1 to 9. Now, let's look at the blue cells, which were these cells. How could we describe 3 complete rows of a Sudoku? Well, that's just going to be 3 sets of the digits 1 to 9. So at this point, we can say the orange cells are 6 sets of the digits 1 to 9. The blue cells are 3 sets of the digits 1 to 9. So any cell that is simply orange and not blue must be, well, no, let's not do it that way. Now let's look at cells that are in both sets. Anything in both sets can be removed from both sides of the equation. Although I haven't really specified the equation yet, have I? So maybe that's what I should do. So yeah, let's go back to that. So the orange cells are 6 sets of the digits 1 to 9. The blue cells are 3 sets of the digits 1 to 9. So the orange cells in total should be 3 complete sets of the digits 1 to 9 greater than the blue cells. But some cells are in both sets, if you like. So this cell, if that cell was a 6 in the finished grid, we could remove this from the blue set and we could remove it from the orange set, and it would still be true to say that the orange set in total is 3 sets of the digits 1 to 9 greater than the blue set. So let's remove this. Anything with 2 colours we can remove, which allows us to remove all of those cells from both sets without changing our conclusion. So our conclusion is still the same. The difference between the orange cells in this grid and the blue cells in this grid is exactly equal to 3 sets of the digits 1 to 9. And we can take comfort from the fact that seems correct, because there's obviously 36 orange cells and there are 9 blue cells. The difference is 27, and 27 is divided by 9 is 3. So the conclusion that I'm stating, which is that the difference between the orange and the blue sets is 3 sets of the digits 1 to 9, does seem to work out mathematically, and it is indeed obviously true if you follow through the logic of what we've just been going through. Now, why do I think this might be interesting? Well, it's because I can now, I think, get some sort of grip on the contents of the orange cells. Because there's definitely, in fact, there's a 9 in there as well. I hadn't seen the 9, but there is a 1 in the blue cells and there is a 9 in the blue cells. So, not quite got my head around what this means, but let me state what I think we've discovered. because the orange cells contain 3 sets of the digits 1 to 9 more than the blue cells, within those 3 complete sets of the digits 1 to 9, there will be 3 digit 1s. Because in one set of the digits 1 to 9, there will be a 1, 2, 3, 4, 5, 6, 7, 8, 9. So there will definitely be a 1 in that set. There'll definitely be a 1 in the second set. There'll definitely be a 1 in the third set. So there will be 3 1s. Now actually, in the blue cells, there is also a 1. So that means that the orange cells need to contain 4 sets of the digits 1 to 9. So this seems good for our Windoku idea. Because wherever we put the 1s, if this is a 1, hang on. No, it's not good for our Windoku idea. No, it's... Whoa. Right. Stop there and take a pause. There are 4 digit 1s in the orange cells. Wherever those 1s are, they are on a 1, 2, 3 renban, because a 1 must accompany a 2 and a 3. So, there are exactly... or at least, no, there are at least 4 3-cell strings in the orange cells, which are 1, 2, 3 strings. So now if I pursue my Windoku idea a bit further, let's see if it works. Let's imagine this was a string that had a 1 on it. So that would be a 1, 2, 3 triple. Let's imagine that was a 1, 2, 3 triple. Let's imagine this was a 1, 2, 3 triple. And let's imagine... sorry, I did that one in the wrong order. I didn't see that was horizontal. And now let's imagine this was a 1, 2, 3 triple. Hopefully it is clear to see that whichever stripe I put the 1s, 2s and 3s on, it's breaking because of the way that the geometry is. This renban line always points at the horizontal renban line beneath it. So if these have the same contents, this cell is never fillable. So you can't put 1, 2, 3, well, you can't put 1, 2 and 3 in each of the 3x3s. That just won't work. So we've got to put 4 1s in this puzzle. Yeah, so you can't even put them in 3 Windoku boxes. Because if I try and put 1s, 2s and 3s into this arrangement, I've still got the same problem. In fact, you can never put them horizontal. You can never put them... Yeah, you can never even put them in those two. If you put a 1, 2, 3 in this box and a 1, 2, 3 in this box, you've broken the puzzle because there will be an impossible digit. 1, 2, 3, 1, 2, 3, this cell's not fillable. So that means that that means I think that you've got to have 2, you've like got an X-wing of 1, 2, 3 renbans. But it's a double X-wing of 1, 2, 3 renbans. So if this was a 1, 2, 3 and this was a 1, 2, 3, then you know you can't put 1, 2, 3 here, you can't put 1, 2, 3 there, so you've got to put the other 2 1, 2s, 3s down here. Now the only thing I'm just pausing about is whether it's possible, and no, it's not. Okay, I was wondering whether you could put 3 1, 2, 3s into a particular Windoku box. That will not work because those 4 cells have to be selected from just 3 different digits. So what we have now learned, which is really, really amazing to me. Why is that 6 there? I don't know. I think that was part of an example I did. But what we've now learned is that we've either got 2 1s and 3s, two sets of 1, 2 and 3 in this 3x3, and 2 sets of 1, 2, 3 in that 3x3, or we've got them in that order. And that's... hang on, you can't have a 1 or a 2 in any of those cells. That doesn't work. This is it. We've actually broken into the puzzle, I think. Right. So, there are, in fact, well, I was about to say there are at least 4 Renban lines with 1, 2 and 3 on it, and that is true. There are no more than 4 because you can't put a whole box full of the digits 1, 2 and 3 for the reasons we looked at before. So there are exactly 4 Renban lines with 1, 2 and 3 on it, and they can't be here, here and down here, because these digits here cannot be 1s and 2s. So we could put a Renban line here to be 1, 2 and 3, but if we're going to try and put a second Renban line, let's try and make this one 1, 2 and 3. How can we do it? We can't do it. We can put 3 in one of the cells, but this cell's now not fillable. It can't be 1 or 2 because there's already 1 and 2 gone from box 7. So I think it's true to say that there is a 1, 2, 3. Yeah, this is good. This is good. It's giving far. This is just a weirdly amazing puzzle. We've got a 1, 2. One of these. Well, no, 2 of these strings are 1s, 2s and 3s. They can't be those 2. Because if that's 2 lots of 1, 2 and 3, we've got this 2 by 2 problem with 1, 2 and 3 again. Those 4 digits have to be selected from just 3 different numbers. So that means, given we know that 2 of these strings are 1, 2 and 3, that must be a 1, 2 and 3. And one of these 2 is also a 1, 2, 3 triple. And the same now, because we know we've got to put 4 Renban lines with 1, 2 and 3 in the puzzle, we've now got to put 2 of these have to be 1, 2 and 3. Again, it can't be those 2, or these cells would just be selected from 1, 2 and 3. So this is a 1, 2, 3 triple, and one of those Renban lines is also a 1, 2, 3 triple. Okay. Okay. So does that mean we have... maybe we think about 9s as well, do we? Yes. Okay. This is a 1-9 pair. That means that within our blue squares we have a 9. The difference between the orange squares and the blue squares is 3 sets of the digits 1 to 9, which will therefore contain 3 9s. So this blue 9 is a 4th 9. That means that there are 4 Renban lines in this puzzle, at least 4 again, but it will only be 4, that have to be 9, 8 and 7. And it's the same logic again. You can't put... I can't make this 987 and then try and make one of those Renban lines 987. It's impossible because neither of those 2 squares can be 987. So that means, again, we're going to have the same thing. We've got the double X-wing on 987s, which means that we need to find a Windoku box that has 2 Renban lines free, which is not these ones, because one of those is a 1, 2, 3 string. So the only way you can do it is by putting 2 987s here and 2 987s here. And that means those 3 squares are 987 and these 3 squares are 987, because otherwise these 2 by 2s have the 2 by 2 problem. So, this is getting awfully close to being broken, I think. I don't know what I've done wrong, but I've just got a horrible feeling that something... I've missed a bit of logic that's crept through the cracks here. Like now I'm looking at the 9 that's in one of those 2 squares. Now one of these lines, I don't know which one, is a 987 Renban line. So the 9 on that line will have to be shifted into one of those 2 squares. So there's a 9 in one of these 2 squares, which means that's not a 9. And that gives us a digit in the grid, because that's on an inequality sign. This can't be a 9, because that can't be a 10. So that squares a 9. Now, does that mean we know anything about 9s in box 1? We know there's no 9 in these cells, so 9 is not in those cells. I'm not sure. I think there probably is a way we can limit 9s more in box 1, but again, it's sort of, it's eluding me a bit how that logic's going to work. So I have made some progress. I've got a 1, 2, 3 in one of these Rembrandt lines, a 1, 2, 3 in one of these Rembrandt lines, a 7, 8, 9 in one of those Rembrandt lines, and a 7, 8, 9 in one of those Rembrandt lines. Right, okay, here's something for you. Those two squares were where we started the puzzle, weren't they? They had red. I remember I highlighted those in red. Now, that's now, I think, forced, because what can we not put on a Rembrandt line down here? You can't put 9 down here. If you try and put 9 in on one of these Rembrandt lines, it will be a 7, 8, 9 Rembrandt and break this square. So that means these two squares have to be a 1, because it's going to be then a 1 that gets forced onto the Rembrandt line. And that's going to give us this digit, obviously. And this digit is a 9 now, and that digit is a 1. So now I'm thinking about the one of these stripes is 1, 2, 3. Whichever one it is, its 1 is going to be in this domino. So there's a 1 in one of those two squares. That's not a 1. That's not a 1. And this is a 1. And this, in fact, this being a 1 means that's not the 1, 2, 3, full stop, doesn't it? So that actually is beautiful. So this is 1. This is a 2, 3 pair. Come on. Good grief. I mean, this, how do you come up with this? Mimaamakim, how do you come up with this? It's bizarre and it's brilliant. It really, I mean, you sort of feel like you're getting a view into someone else's brain, and what's there is absolutely terrifying in terms of its genius. It's just, but it may be brilliant. It may be too brilliant for me. 9 is in one of those. How did I get the 9 here? Oh, by getting these. So that's tidied up my 9. I get a 9 there. That's beautiful. Because once you get a 9 on a Rembrandt, that's a 7, 8 pair. So we've got 7, 8, 9 here. We've got a 7, 8 pair. Oh, 9, 9. Where does 9 go in that box? You can't put 9 here. You can't put 9 on the Rembrandt line, where it would be a 7, 8, 9 and definitely break those two squares. So 9 goes up there. Which means, yeah, okay. So that means 9 in box 3 is in one of those cells. Which means, oh. It means that these two squares don't include a 9. But we don't know whether it's 7 or 8 that accompanies them, do we? So I'm not sure we do get any restriction on that digit. I sort of feel like, I'm not sure we do. So what on earth do we do now? I haven't got a clue. I have not got a clue. Do I have to think about the blue cells? So I've got the orange cells differ from the blue cells by 3 sets of the digits 1 to 9. So I know that I've got a 1, 2 and a 3 in the blue, which makes sense because I know I've got 4 Rembrandt strings that are 1s, 2s and 3s. I've got 1, 9 in the blues, so that must be 9, 8, 7, which corresponds to the 4, 7, 8, 9s. So there must be an 8 and a 7 in those cells. But then I don't know that we know. For example, this Rembrandt line here. Do we know what that Rembrandt line is? Have we got even an inclination what it is? We know it's not 7, 8. Oh, I suppose those digits are a little bit restricted. Right, hang on. These digits are not 1, 2, 3. So they can be 4, 5, 6. They can't be 7, 8, and they can't be 9. These are just 4s, 5s, or 6s. Yeah, okay. So where do we put 2 in column 2? That's a good question. You can't put 2 on this Rembrandt line, or you'll definitely need a 3 on it because it's a 3-cell Rembrandt line, and you can't put a 3 on it. So that's not a 2, that's not a 2, which means that's a 2. This means what? Don't know. I really don't know. The video's getting longer and longer. This, I think, could be a very long video. This is a fascinating one. It really is. I've got a horrible feeling that we're going to have to sort of work out. We know that's not 1, 2 and 3. We know this one is... Do we know... How many Rembrandt lines have we got? We've got 12 Rembrandt lines. And we know the composition of 8 of those Rembrandt lines because we know we've got 4 1, 2, 3s and we've got 4 7, 8, 9s. So there are 4 Rembrandt lines that we don't know about yet. But we do know that those 4 Rembrandt lines have to include 3 4s, 3 5s and 3 6s because we know that the orange squares differ from the blue squares by 3 complete sets of the digits 1 to 9. That means they've got 3 4s in them, 3 5s in them and 3 6s in them, and I have not allocated those to Rembrandt lines yet. So we've got to put 3 6s at least on Rembrandt lines. How do we do that? We've got to put 3 6s at least on Rembrandt lines. And we've got to put 3 4s at least on Rembrandt lines. Does that mean... what you can't do though, I was wondering whether we could have sort of 4, 5, 6 Rembrandt lines, lots of those, but that's not going to work, is it? Because if those 4s, 5s and 6s happen to be on, so we know there's 3 4s, 3 5s, 3 6s, if they are all on the same Rembrandt lines, i.e. they're 3, 4, 5, 6 Rembrandt lines, if you see what I mean, that won't work, because There's no way of, like, if that's a 456 rem band line and that's a 456 rem band line, this has got no fill. So that doesn't work. And if we're going to try and put 2 more rem band lines in that are 456, we can't do it, because one of these would have to be a 456 rem band line. That's going to break those squares. So you can never have 3 456 rem band lines. I appreciate this is complicated, but it's like you have to imagine that I'm spelling out the word 3. It's like you can never have THREE and then the numbers 456 rem band lines, if you see what I mean. You can't have 3 456 rem band lines. So if you have, but you have to have 3 6s on rem band lines. Right, how about this then? Does this work? If you've got to have 3 6s on rem band lines, and you do, so 3 of the 4 remaining rem band lines must contain a 6. How many low rem band lines of those 4 rem band lines? How many contain a low string of digits? I.e., a set of digits that don't have 6 on it. It's exactly 1, isn't it? So there can be a maximum of 1 rem band line that is from a low set of digits, which could be anything that doesn't have a 6. So it could be 3 4 5 or 2 3 4. But it can't be 1 2 3, because we know we can't have any more 1 2 3 rem band lines. But the same is true in the other direction, isn't it? There are 3 rem band lines that have 4s on them. So the maximum number of rem band lines in this puzzle, or the maximum number of the 4 remaining rem band lines in this puzzle that can be selected from higher digits, i.e. digits that don't have a 4, is 1. I could have a 5 6 7 rem band line, or a 6 7 8 rem band line. I can't have a 7 8 9 rem band line, because that's not going to work, because that would be a 5th 7 8 9 rem band line. So given that I can't have 3 4 5 6 rem band lines, and I can't have more than 1 rem band line that doesn't include a 4, and more than 1 rem band line that doesn't include a 6, I must have 2 rem band lines that contain both of those digits. That's forced, that's logical. And those, if you have 2 rem band lines that contain the digits 4 and 6, they must be 4 5 6 rem band lines. Let me just check that's true. Hang on. If we try and have 3 rem band lines, no, you can't. I think that is right. It's slightly hard for me to articulate it. I can sort of feel it's true, and I'm trying to articulate it as best I can, but we've got to have 3 rem band lines that have 6s on them. We've got to have 3 rem band lines that have 4s on them, at least. Therefore, if you were to try and have a low rem band line with no 6, you could do that, but you could only have 1, because the other 3 rem band lines would need to have 6s on them. But the same is true the other way round. If you try and have a low rem band line, you can only have 1. Sorry, if you have to try and have a high rem band line, you can only have 1, because 3 of the rem band lines need to have 4s on them. So that means that two of your Renban lines must contain both of those digits. That's what I think anyway. I think that's true. I'm sorry if everyone's going, yes, of course that's true. But when you're in the middle of a puzzle like this, and something might turn on it, and the whole 45 minutes might be wasted, you have to bear with me if my little old brain doesn't quite believe it. I feel like I should spend a bit more time just really making sure that I believe this is true. Yeah, so you can't have more than one. Yeah, and it's tied together with the fact you can't have three Renban lines that are 4, 5, and 6. So the maximum number of Renban lines you can have with 4 and 6 on them is 2. But if you didn't have 2, you'd break one of the other sets, wouldn't you? If you didn't have 2 and you just had one 4, 5, 6 Renban line, yeah, you'd have too much trouble with the other 3 Renban lines trying to make sure that you still had three Renban lines that contain a 4 and 3 Renban lines that contain a 6. I am comfortable with that. So, what have we done? We have learnt that there are 2 Renban lines here that are 4, 5, 6 Renban lines. This looks like a very likely candidate, doesn't it? Yeah, actually, well, one thing I've just thought of is that if this is a 4, 5, 6 Renban line, that can't be a 4, 5, 6 Renban line. So if that's a 4, 5, 6 Renban line, you can't have a 4, 5, 6 Renban line in those 2 squares. So that, again, you've got an X-wing on 4, 5, 6 Renban lines. Right, this is beautiful. Yeah, I can do this. We know, because I've just proved it in my brain, that there are 2 4, 5, 6 Renban lines. We know they have to be diagonal. Well, the simpler thing to do might be to just consider, can either of those be a 4, 5, 6 Renban line? The answer is no, because those cells will break. So there are no 4, 5, 6 Renban lines here. Ergo, there are no 4, 5, 6 Renban lines here. And the 2 4, 5, 6 Renban lines which need to be in an X-wing arrangement are this one and one of those 2. So that is a 4, 5, 6 Renban line. This square at the bottom is now a 3. Oh, well, this is huge, because neither of those squares can be a 2. 2's have gone in the column, so this is a 3, 4, 5 Renban line. So this is the Renban line that doesn't have a 6 on it. Every other Renban line in this grid has a 6 on it. One of these is a 4, 5, 6 Renban line. So whichever one it is will have to have a 6 in this row, look, because it can't be a 4 or a 5. There's a 6 in one of those 2 positions. One of these is 4, 5, 6. And then up here there's a Renban line that's got a 6 on it. But doesn't have a 4 on it. Because if it did have a 4 and a 6, it would be a 4, 5, 6 Renban line and break these squares. My goodness me. Okay, so there is a Renban line up here that is either 5, 6, 7 or 6, 7, 8. Right, this is so beautiful, I cannot tell you. This is just ridiculous. Right, try this logic then. One of these Renban lines is the partner of the 7, 8, 9 here. So there is a 7, 8, 9 Renban line in one of these 2 strings. The other Renban line contains a 6 but not a 4. So it is either 5, 6, 7, which has a 7, or it's 6, 7, 8, which has a 7. So both of the Renban lines in this string of digits has a 7 on it. And that means in box 1, neither of those squares can be a 7, and that's a 7. Ta-da! This gets me a 7 here, and an 8 here, and an 8 here, and a 7 here. I don't know if this is going to go much further, but it's quite exciting. So now, this square's not a 7, but we've got beaucoup de sevens we've got to put in this. How many? We've got to put 3 sevens into this Windoku, which I know is not really a Windoku, but that's how I've been thinking about it. So, yeah, okay. Look at the remaining 8 cells of the Windoku here. I know I've got to put 3 sevens in because I've got a 789 Renban, I've got another 789 Renban somewhere, and then I've got the Renban that's got a 7 on it that doesn't have a 4 on it, that does have a 6 on it. So that means there are 3 sevens in those 8 cells, but those 8 cells are in just 3 boxes of the Sudoku. So then those 7s must be allocated like that. There must be a 7 in this domino, a 7 in this domino, which we already had, and a 7 in that domino. Right, that gets me the 7 in column 9. Because I know there's a 7 here, I know there's a 7 here, so there's no 7s in those 6 cells. No 7 here, so that's a 7. One of these 2 cells is a 7. And okay, 7, 8, 9. Okay, and that's all great, but it's not actually finished the puzzle still, has it? Although I do think we're sort of getting a bit closer towards a solution. There must be an 8 in this domino, and that 8 will correspond to whichever Renban. Oh, right, I now know the contents of the Renban lines. Yes, right, let's look at this. So, I know there's an 8 in one of those 2 cells, so it's not possible that these Renban lines are a 789 Renban line, which one of them is, and also an 876 Renban line, because that will remove the possibility for there to be an 8 in box 1. So the other Renban line here must be 567. So those squares are 5, 6, 7, 8, 9. One of them is 5, 6, 7. And one of them is 7, 8, 9. And probably you're all shouting at me because you can see how to do that, and I can't quite see it. So now, I suppose, we know the composition of the blue cells, don't we? I'm just wondering if that's the way to get back into the puzzle again. So, the blue cells differ from the orange cells by 3 sets of the digits 1 to 9. So which digits do we have 4 of in this puzzle? We have 4 1s, 4 2s and 4 3s, which we've already catered for. We have a 5th 3 here. So there has to be another 3. Yeah, that's quite interesting. There has to be another 3 in blue. Now that 3 can't be in those cells, so one of those 3 cells is a 3. We've got to have a 7. We've got to have the 7 and the 8 that corresponds to the 7, 8, 9 triple. So we've got to have an 8 and a 7. Sorry if you can hear shouting outside. At least I haven't been called to go and address that yet. That's definitely making me lose my train of thought. So there was definitely a 7 and an 8 in the blue squares. And then we've got to think about the other Renban lines. So we've got the 4, 5, 6 doubled. We've got the 4, 5 here. We've got the 6 from up here. So we've got 5, 7, and 3. Yeah, okay, so we've got 5, 7, and 3 to go along with our 7 and 8. So these squares actually we now know are 3, 5, 7, 8, but there's 2 7s. That's not 7. That's not 7. I can't put 7 here because that will eliminate my ability to have 2 7s in the remaining blues. So that's not 7. I believe those two are 7. There, I've said it. That 3 now must go in the middle. This is just ridiculous. Whoops, whoops, whoops. I didn't mean to do that. Okay. Has this done it? Don't know. That felt like a breakthrough, but maybe it's not. So there's a 7 in here, a 7 in here. Yeah, the 3 7s that are remaining are the 7s around the top right Windoku. This 3 is powerful. That's giving me a 2 there, and a 3 there, and a 3 there, and a 2 there. So that square's now become a 1. That feels like it might be important. Ooh, yeah, okay. Where do you put 1 in this box? It can't go there or there, so it's in this domino. Well, the inequality sign is quite important then, because it can't be there, because that would have to be a 0. So that's a 1. 1 comes out of here. Oh, this is beautiful. Right, now we're getting excited, because this, we know that there's a second 1, 2, 3 in this Windoku. Well, it's now not there because of this 1. So it's here. This is a 1, 2, 3 triple. That's not the 1. That's not a 3. It's definitely not a 6. One of these was a 6. We now know it's this one. We know that this is the 4, 5, 6 that corresponds to this one. So we've got 4 and 5 into those squares. We've got no 5 up there. We've got... I don't know what else we've got, but it seems like we almost have something. We've got... don't know. We've got to put a 3 in one of those cells. We've got to do... What else have we got to do? Where does 8 go in box 9? It's got to go in that domino. Which means 8 has to be here in box 8. That's helpful. That does that one, which we know is the counterpart of that one. So that becomes an 8. That gives me a 7, 9 pair here, so this becomes an 8. Keep going, go on. 8 must go here by Sudoku of all things. Fancy doing Sudoku in a Sudoku puzzle. How ridiculous. Okay. 3 is fixed in this box. Those 3s lock in. This square here is a 3, so this is a 1, 2 pair. Which might... Oh, 2. 2 is now locked in box 6 as well, so that's a 2. That's a 2 by Sudoku. How many 2s have we got? The answer is many, but not all. That's a 2. Let me just take a stare at this. Can we do better? I feel that we probably can, but yet again, I'm not quite seeing how. I can place 1 in box 8 just by Sudoku. That 1 is nice. 1 and 2, 2 and 3. I might have... Have I done all the 1s? Yes. Have I done all the 2s? Yes. Have I done all the 3s? No, but I might be able to. That's a 3, that's an 8. Go on, keep going. Yes, this is a 3 now, yes. 8 here. 8 here is powerful. Look, it's getting rid of 8s up there. This square's a 4 or a 5 by Sudoku. That square's now known. That's a 6. Which means there's a 6 on this Renban, which means that's not a 6. This square's got to be a 4 or a 5. That means this square's a 6 to complete that column. 6 is vertical in column 5, which doesn't do what I was hoping. Oh, but 6 is in one position, I think, in this box. I think it's got to go there. which means that's a 6. This square here has got to be a 4 or a 5. I hope you'll forgive me if I take my time over this. I really don't want to make a mistake on this beautiful puzzle. I need 4s and somethings. 4s and 9s in this column. Can we do that? There's a 9. Yeah, there's a 9 there. So that's got to be the 9. That's got to be the 4. That gets me a 5 here. Now I know this is a 4-6 pair. That square's a 4 by Sudoku. These squares are now known. They are a 5 and an 8. But I don't know if that's resolved. Let's get rid of the 6s. Get rid of the 8s over there. These two squares here are 4 and 6. Don't believe it. I don't believe it. Those two squares then, they are 5 and 9. I can do those. That's 9. That's 5. So this is 4, which means that's 6. That's 4. 6 comes out of all of these cells on the funny renbands, which feels like it should matter, but I can't exactly see how. This 4 is giving me a 5 here, so those squares go in. That bounces back over here, which bounces back over there. It's completely nuts. Doesn't there have to be a 6 on this renban? Well, now there does, and we can see where it goes. We know that there was a third 6 renban. It's now not this one, so it's this one, and we know it's a 5, 6, 7 triple. So this is a 5, 6, 7 triple, which means that square's an 8. That's a 5. Oh, this is horrible. What if I've got this wrong? 7, 9 here. 6 means this is a 5. That's a 7. That's a 6. That still looks like it's working. Please. Oh, that's got to be an 8. I don't like the look of this at all. I need something to disambiguate. Oh, this 9 might do it. 7s, 9s, 9s, 7s. This column needs a 5 in it. That gets me 5s and 4s. And this square is a 6. Have I done this puzzle? Yes, I have. I'm quite proud of that. Whoa. What? What have I just solved there? That is one of the most surprising, weird, innovative puzzles I have ever solved in my life. Full stop. Let me just get rid of the highlighting there, because I sort of think it's polluting the idea, which is to do, I think, with the fact that these I keep calling them Windoku boxes. You can see they're anything but. There's a 1, 2, 3 and a 4, 5, 6 in this one. There is no 7, 8, 9. So in none of these is there a 1, 2, 3, 4, 5, 6, 7, 8, 9 window. But it is so minimalistic. So Mimaamakim has used the sandwich clues to put a very specific arrangement of digits. I think in this box, I think it's those 3 digits that Mimaamakim was sort of focusing on, because those 3 digits allowed us to understand, combined with the fact these were a 1-9 pair, that there had to be 4 1s and 4 9s in these strange renban arrangements. And because you couldn't put a second 1, 2, 3 renban down here, that actually got a lot of progress in terms of the positioning of the 7, 8, 9s and the 1s, 2s, 3s. Now, the hardest thing for me about this puzzle was thinking about the 4 renban lines that we didn't understand. So the 4 renban lines that were not 7s, 8s, 9s or 1s, 2s, 3s. And there, I really had to think quite hard and repetitively, and I apologise for that if it ruined the video for you. I really hope it didn't. But I had to convince myself that there were two sets of 4s, 5s and 6s. And I think that there are. And that logic derives from the fact that there can't be 3 4, 5s and 6s, because if there are, you can't arrange them in this strange renban pattern, because one would point at another and rule it out. And if there weren't then 2 4s, 5s and 6s, and there was only 1 4, 5 and 6, you wouldn't be able to fulfill your quota of having 3 6s on Rembands and 3 4s on Rembands, which must exist because the orange squares are 3 sets of the digits 1 to 9 greater than the blue. So you know that there are 3 4s, you know there are 3 6s on the Rembands. It's startling. It is absolutely startling that this puzzle has a unique solution, and also that unique solution has been done with such minimal clues. These 2 inequality signs and a couple of sandwich clues around the edge is enough to make these Remband lines work magic. What a puzzle that is. I will not forget that puzzle. That is ridiculous. One of the best puzzles we've ever had on the channel. I know it's a long video. It's a Sunday night though. There's never anything on TV on Sunday nights. So Cracking the Cryptic takes the place of Netflix, whatever it is. And Mimaamakim showcases one of the greatest puzzles we've ever seen. Thank you so much for bearing with me and watching it. And we'll be back later with another edition of Cracking the Cryptic.